Okay, so now on to chi-square tests, which I'm sure you remember from your statistics classes. We're not really I'm gonna give like one example. We're not gonna go into a lot of detail with the math, but again, as per the hypothesis testing in chapter two, week two, we're just gonna try and do enough so it can link what we do to your previous knowledge. So we have a situation here, and what we want to do is it's kind of a little brand identification example. So say, for example, I'm a cell phone gaming company, and I'm worried that I have low brand awareness among females. So I want to test that brand awareness, and I want to see if there's some sort of linkage between gender and brand awareness. Brand awareness being conceptualized by who can identify my product and who can't identify my product. So literally, all we do is we're going to get 145 males, ask them if they could identify or not identify, and we've got 155 females, could identify, could not identify. And then we tally up the totals and put them in this table. Notice we have row totals, and in this case, the row totals are the people who could identify the product and could not identify the product. And we also have column totals. And the column totals are basically the number of males and the number of females. So the idea here is if there's some association between gender and the ability to identify the product, then we're going to see some sort of patterns in the data. And we really can here, males almost 2 to 1 could identify the products. Females, it's like 2.5 to 1 could not identify the products. So just common sense, we think there is some association there. But we want to show it mathematically. And how do we do that? Well, let's just put the numbers here, which is the row totals, which is a could and could identify product, the column totals, could and could not identify male and female, and then the total n. Now we can convert all these numbers into product probabilities just by dividing by n. And so we get here that this would be the probability that that somebody in our experiment is a male who could identify the product, a female who could identify the product, a male who could not identify, and a female who could not identify. And the idea is if we're independent, so let me just kind of write this down. So I'll do it on the pen. Okay. So let me look here. So if we're independent, two probabilities are independent. Then the probability of both of them happening, so the probability of, say, A happening and the probability of B happening, do you remember this from Business Stats 1, is basically the multiplication of PA and PB. You multiply the products together. This only happens if they're independent. So say, for example, what's the probability of your professor being a nice person and your the probability of your professor having ginger hair, red hair? Those guys should be independent. There shouldn't be any relationship between the two categories. Now, let's just have a look here. And imagine we have row I and column J. Now, the probability that I'm on row I and in column J, i.e., say this is 1 and 1, I would be like here. Or there is going to be the probability of I times the probability of j. Yeah, just the two independent probabilities. The probability of these guys should be like proportionate if we're independent. So this could be proportionate to the number of males times by the people who could identify. Now, we also know that Pij, the probability of being I, kind of in row I, is the row total for I all over the number of n. And for column j, that's going to be the column total all over n. So we get row I times Cj all over n squared. But for n items, the expected number that we're going to get in row I and column j is just that times n. So it's going to be Pij times n. You know, each item has this probability, so we do it n times, we multiply it by n. So that's just going to be row I, column j, all over n. And essentially all we're doing in this chi-squared test is this is our expected value, and we're seeing how far away we are from this expected value. So let's go to the slide, so the chi-squared test slide. And this is our chi-squared test. Our null hypothesis is that you can either say independent or they are not associated. And the alternative hypothesis is they're dependent or they are associated. Our chi-squared statistic basically says our individual cell counts, how different they are from the expected values. And then we know we square that because otherwise everything would cancel out, and we divide it by the expected values. And then we test this. This is considered to be distributed to something called the chi-squared distribution. And then we test if it's significant. If it's big enough, you know, if our values are far enough different from their expected values, then we got evidence that we're dependent. Now, what are our conditions on this test? Well, we need to have random samples, and B, the expected cell counts, our expected values, should be greater than 5. If they're not greater than 5, then we have to do something called a Fisher's exact test, but we'll talk about this later. So let's go through our little example. And what I'm going to do is I've actually got the data here in Excel, and I've actually got the calculation here in Excel, but we're going to go and do this through this manually. Okay. So let's take the screenshot again. And let's just make that bigger. Okay, that didn't work. That's okay, that will do me. And we use our red pen again. Okay, so we're testing kind of the dependence of Brown. So we'll start off here. And our null hypothesis, so our kind of hypothesis, that is that kind of, we'll call this could identify, could not identify. We'll just call it brand awareness. And gender are independent. And the alternative hypothesis is the brand awareness and gender are dependent. My test statistic is the basically chi-squared, and basically for each of our rows, and we'll just say we have little r rows and little j columns. This just means we're cycling over both the rows and the columns. It's the number of observed in that cell minus the expected value of ij squared all over the expected value of ij. And I'll reject h naught. We're going to reject h0 if chi-squared is greater than the critical chi-squared value. Now the chi-squared value, let's just draw a chi-squared distribution. As chi-squared gets bigger, we basically have more and more evidence. We're more and more different from independence until we hit the critical region, which, say for example, our type 1 error is 0.05, i.e. assuming the null hypothesis is true, we have this 0.05, this 5% chance of making an error. So basically we kind of get more and more evidence until we finally reject. We go more evidence, and then we finally reject. Now this has a degree of freedom, and the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. Now here, this is really easy. This is just 2 rows, 2 columns, so it's 1 times 1 equals 1. I remember the degrees of freedom, it's the amount of data, the amount of data values we have, and then kind of subtract for each kind of parameter or piece of additional information we have. So in the end here, we just have 1 degree of freedom. And you can actually look these up at the tables of your back of your business stats book. But say we have a 5% error, which is the chance of rejecting given the null hypothesis is true. In this case, it's going to be 3.84. As this guy gets lower, then we essentially get bigger and bigger test statistics. It's harder for us to reject. Okay, let's kind of erase all link. Now, so we need to calculate this. So let's just do the expected values. Before we do the chi-squared, we need to I should have removed my mail. We need to calculate the expected values. So let's just say the expected values of row 1 and column 1. This is going to be the row total for column, the row total for row 1 and the row total for column 1 divided by my n. This is going to be 136 times 145 divided by 300, and it's going to be 65.733, which is this value here. So I've got the Excel spreadsheet that basically calculates everything. So row 1 and column 2, it's still going to be 136, but this time we're 155 is my column, divided by 300, and that's going to be 70.2667. Row 2, column 1 is going to be, again, this is 164 times my 145. 79.2667, and expected value of row 2, column 2 is going to be 164 times 155, the only combination we've not had yet, and that's going to be 84.733. So my actual chi-squared, my calculation, is this kind of sum of the observed value minus the expected value squared. So let's just have a look. The first one, I observe 95 minus 65.733 squared all over 65.733. The next one is going to be row 1, column 2, and that's going to be 41. And you can see here there's quite a deviation here because obviously my data is are not very independent. We've got far less females than we would actually expect. And then my next, I'm going to have to write a little bit smaller. So this is going to be row 2, column 1. That's going to be 50 minus, and again, males who cannot identify are kind of underrepresentative. But females who could not identify are overrepresented. So there we can see here that there is some association. Whoops. So that's 114 minus 84.733 squared all over 84.733. So my final chi-squared is 46.135. Now that's greater than 3.85, which is my critical value. So we're going to reject H0. There's evidence for association. Now, just I'll give you a second if you're writing that down. Kind of just going again back to my chi-squared. So again, this we assume H0 is true, and then we have this type 1 error, which is given H0 is true, the chance we reject. So we've got this again, we have this trade-off. So let's just say this was 0.05, and this was a chi-squared alpha, or not, which is 0.05. Let's get a different color. Let's go with a nice blue. Now say we have our chi-squared. The value to the right here is my p-value. And so as my chi-squared gets bigger and bigger and bigger, my p-value gets smaller and smaller and smaller. And when we hit this critical chi-squared value, my p-value is 0.05. So what we did before, our chi-squared is bigger than the critical. It's equivalent to say we're going to reject if my p-value is less than alpha. So again, in R, we don't have to kind of worry about critical statistics. We just say R will actually calculate the p-value for us, and we reject if the p-value is less than alpha. Okay, so let's go back to this example in R. So, where were we? Okay, so we're going to read in our brand table, and we're going to require a package called reshape, I'm going to say in a minute. And, okay, so we kind of read in our brand information. And you can see here that we've kind of, this again is in the long format. We've got a frequency for each combination of gender and identify, whether they could identify the brand or not. Now we're going to use a function called dcast. And what dcast does is takes this data set and it creates a table based on identify and gender. We just got identify, and again it's our formula squiggle and gender. We can see here what this does. And we have identify, no or yes, and then we have the brand ID, female or male. And we can get the row names. Let's just have a look at this. The row names are no and yes. So let's just have a look at the brand table. And then we have identify, don't identify, identify, female and male. And then we just have to, we want to put it in the as.table format, just the table utilized by the chi-squared test again. And again, we're not going to take this identify column because that's just a label. So what we're doing is we're basically, the label was in the rows, but we're actually turning it into an explicit row name, no or yes. And now, once we've done that, we're removing this identify column. So you see we're taking columns 2 to 3, the ones with the numbers in them. We're turning it into a data matrix and then into a table. And again, this sort of stuff, if you're trying to do it yourself, is hard. So just play around with my code a little bit. But this idea of converting between formats should get more natural as you go along. And then we have the brand table. Okay, so the chi-squared test, basically run it using chi-squared.test. We put in our just put in the table, and there's something called Yates's continuity correction, which affects for the fact that we're turning something discrete into something continuous. But we're not going to worry about that. We're just going to use the basic chi-squared test. So we say our p-value, and this was really, you can see just by the ratios that this was really strongly associated. So we kind of reject the null hypothesis of independence, and we have this like incredibly low p-value, which is lower than any alpha we can find. But we could, if we wanted to, we could actually just say, okay, our chi-squared is 46. What's my critical region? The Q, remember Q gives us the distribution function. So this time it's Q, before we did QT and Q norm, this time we're doing Q squared. Again, we're going left from right, so we want 0.05 to the left, so we've got 0.095 to the right. Degrees of freedom, as I showed you in the example, was wrong. And there we go, that's our critical value. Okay, so let's have a bit of fun. Let's have a fun little data set. Or not so fun. That's funny. This is the passenger log from the Titanic. So let's just kind of view that data set. And we literally have basically every passenger on the Titanic. And this is the real passenger list. So we have the gender, the sex. We have their age. We also have the class they were in, the cabin class. You know, we have first class, second class, and third class. And we have whether they survived or not. And so we have these interesting categorical variables. We want to say, you know, is gender associated with survival? And this is a real data set. If you read the history of the time, it's interesting that these guys just caused them. This guy, Colonel John Jacob Astor, was like one of the richest people in America, and he basically caused a major societal scandal. He just divorced his wife and then married somebody who was much younger, female, and this was kind of apparently a major society scandal at the time. So this is the real data from the Titanic. Okay. So how do we do it? Well, let's just remember, going back to what we did at the beginning, we can actually create a table. So let's create a table between class and survived. And we can see that in first class, at the top we have survival 0 or 1. In the first class, nearly twice as many people survived as didn't survive. But in the third class, the majority of people perished, i.e. there wasn't enough lifeboats. So that's like a little bit, you know, there weren't enough lifeboats for the third class passengers. Now let's run the chi-squared test. And you can see that we have a big data set. We have a lot of evidence. And we see they have this incredibly small p-value, which is the amount of the lowest p-value R can do because it's such strong evidence. We have a chi-squared of 127. Degrees of freedom is 2. We have 3 rows minus 1, 2 times 1, 2 columns minus 1 times 1 is 2. Now, there's something here that's called the Kramer's V. And what the Kramer's V is what we call an effect size. because with a statistical test, as n gets bigger, we get more significant. Which means we could have a really small, with a big N, we could have a really small significant. We could have a really small effect, but we have a big enough N that we get a significant result. So what the effect size does is it basically gives you, it tells you how strong the effect is. So it's how strong is the effect. Independent of N. And the Kramer's V is the square root of the chi-squared. So again, we divide by N. So bigger N's we divide it by more. And we multiply it by M. Now what's M? That's just the minimum value of r minus 1, rows minus 1 times columns minus 1. So in this case, we have 2 columns, so that would be 1. And that's going to be the number of items. Now, don't worry about this. This isn't going to be on the exam or anything, but just the actual calculation. But just realize this is between 0 and 1. And the closer we get to 1, the stronger the effect. Now let's go back to our R. So my Kramer V is 0.32, which is actually, you usually say 0.1 small, 0.3 medium, 0.5 large. That's quite a decent effect size. So now we're going to do the same for gender and survival. And we can say, whoa, you know, like surviving females to males was 3-1, but it's more than 4-1 in the opposite direction. The females, maybe it was a more gentlemanly time, but the females had more precedence on the lifeboats. So we run the chi-squared test. And again, you can imagine this is incredibly significant. You know, there is this big relationship between gender and survival. And we calculate the Kramer's V, which is 0.5, which is very large. Okay, let's do one more example. Let's go back to our housing data. So let's just say, is there a relationship between the type of housing and whether or not it has central air? And we see here that it's interesting. It's kind of, there's a lot of yeses, a lot of nos. For most houses actually have central air, and you can see here that there's about at least probably a 10-1 ratio. But you see here, you know, these townhouses, they're all modern houses, so every one of these actually has central air conditioning. So we can run a chi-squared test. And we can see it's very significant. But there's a bit of a problem here in that we might expect, because if we think of a house in a very, you know, a category with only a few items. So this category, for example, has very few items, and only a few of them are not going to have central air. Some of these expected values might actually be less than 5, which means we can't use the chi-squared test. In this case, we use something called the Fisher exact test, which basically works through the individual kind of combinations of rows and columns. And that doesn't have that assumption. Now, to run a Fisher's exact test on this big data set would take days and days and days. And R gives you an option to do a simulated test. And all this does is it makes it a lot quicker. And Fisher's exact test, so very similar to the chi-squared test. And we have a very small p-value. And again, we have evidence that there's some association between housing type and whether it's having central air or not, which is obvious from the data. You know, the townhouses are all new, so obviously they all have central air. Just one final point, some of these data sets, most statistical tests rely on a random sample. Now, the Titanic, we're almost saying we've got a random sample of passengers or random sample of passengers from cruise liners that may or may not sink. So it's possibly not a random sample because it's every single person on the ship. But we don't have to be very strict with this, and it does give us an idea, this chi-squared test, regardless of our sample being completely random or not, how strong the relationship is between the categories. And we could see, for example, the gender and survival and the class and survival were incredibly strong relationships.